Hello and welcome back to the second half of Module 3. So last week we talked about the law of mass conservation, the law of definite proportions, and this week we're going to look at the law of multiple proportions and Dalton's atomic theory, which is actually an assumption. Okay, it's not a law. Sometimes in nature we have elements that combine to make us different compounds. So the same kind of elements can combine to give us different compounds. The example they give you here is carbon monoxide versus carbon dioxide. Both of them have carbon and they both have oxygen. As you can see, carbon monoxide has one oxygen and carbon dioxide has two oxygens. So same composition chemically, but different number of atoms, making them behave differently. So the fact that we have compounds that act this way will help us understand the law of multiple proportions. So you're going to learn what that means based on compounds that act this way and how to use this knowledge to do some problems this week. So what does this law say? That's on page 82. If two elements can combine to form more than one compound, like we did with carbon dioxide and carbon monoxide, here we have nitrogen monoxide and nitrogen dioxide. So different compounds, different atoms, different molecules. So if two elements can combine to form more than one compound, the masses of one element that combine with the fixed mass of the other element are in ratios of small whole numbers. Mouthful. What does it mean? Nitrogen, nitrogen, oxygen, oxygen. So both of them have chemically the same kind of atoms. But this one, nitrogen monoxide, only has one atom of oxygen, while this nitrogen dioxide has two. The fixed atom is the nitrogen. Both of them only have one. That's called the fixed atom because it's the same in both molecules. Both compounds have the same, only one. What's different? The number of oxygens. So if you compare those, 1 to 2, okay, 1 to 2 is a ratio. You can write ratios like these or with two dots, 1, 2 dots, 2. And we'll see in a minute how that works. Don't look at this one right here, just at the nitrogen because that's the example I have right here. Another way of saying this, the law of multiple proportions is telling us that whenever two elements form more than one compound, which it happens a lot in nature, okay? Those elements, carbon and oxygen can combine in different amounts, carbon and hydrogen in different amounts, and they all are different compounds that behave differently. But the composition, the elements that make them up are the same, just changes the number of each. So when that happens, one element that combines with the same mass of the other element are in ratios of small whole numbers. 1 to 2 are whole numbers. There's no decimal points or fractions here. It doesn't matter what you have. This is the element that's fixed, doesn't change from one compound to the other. A is the one that changes in proportion. So what is the ratio? 1 to 2. 1 to 2. You see how they produce different things? C and D represent two different molecules because if you change the number of atoms, you change the number of the nature of the molecule. But this is a ratio, and remember you can also do it as a fraction. And this ratio is in whole numbers. This is what this law says. Now, John Dalton's atomic theory is based on the three laws that we have learned. I'll show you another slide that has that information in it. But what did he say, this man? This is in the 1800s, so we're moving along in our knowledge of matter. That's found on page 83. These are assumptions. That means he was never able to prove what he said. He just was doing experiments and he said, well, if I believe this explains my experiments. But he didn't have a way to prove his assumptions. And in a minute, we'll see that he was wrong in some of his assumptions. But that's how science works. I mean, they have new discoveries, they found new technology that helps us change how we believe things to work, and we move on. But he was a contributor to how we understood how matter worked and how atoms work and so on. So we're going to study him. He said, all matter is composed of small particles called atoms. Okay, great. All atoms of a given element are alike. Compounds are formed when different atoms combine in fixed proportions, and a chemical reaction involves the rearrangement of atoms. So for assumptions, you need to know what he said. Now, his assumptions were based on the laws he knew about, the law of mass conservation. Lavoisier came up with it, but you don't need to know who came out with it, okay? You just need to know what each law says. Those two we covered last week, so I'm going to read them again. But the law of mass conservation said that the total mass of a substance that does not change during a chemical reaction, because what comes in must come out in mass, okay? The law of definite proportions is also called the law of definite or constant composition, because no matter what its source, a particular chemical compound is composed of the same elements in the same parts or fractions. You remember that? We need recipes to form compounds. They are always in the same proportions to make the same compound. The law of multiple proportions, we just talked about it today, is when two elements form a series of compounds, so they can form more than one compound. The masses of one element that combine with a fixed mass of the other element are in the ratio of small integers to each other. So when you compare them, those are whole numbers. He said that, Dalton said that. And all three help him develop this atomic theory, which is assumptions. Now, he was incorrect. Two of his assumptions are incorrect, right here in red. He said all matter is made of extremely small particles called atoms. We agree, that's true. Okay, the smallest particles are called atoms. All matter is made out of atoms. Great. All atoms of a given element are identical, and we'll see that that is not true, having the same size, mass, and chemical properties. Atoms of specific elements are different from those of any other element. Well, that part is true. If you look at your periodic table, every single box contains a different element, and they are different because they have different atomic numbers. So the number of protons they have, okay, is different, and that makes that element have different properties than the element next to it, and they increase in numbers of 1. So you have, if you go to page 75, we'll start this in more detail, but if you go to page 75, you'll see that in box number 1, you have hydrogen. In number 2, you have helium. Number 3 is lithium. Then you have beryllium in number 4, and so on. So you go from left to right, and then from up to bottom, and increase the number of 1. And those are the number of protons that will become the number of electrons. But he didn't know anything about electrons or protons and neutrons. He had not learned about that yet. That has not been yet learned. So he didn't know that. He did know that they acted different, and he thought all of them inside that box were the same. But we'll see that some of them have different masses in a minute. Number 3 was also wrong. It says atoms cannot be created, divided into smaller particles, or destroyed. Well, we just said that we have protons, neutrons, and electrons. We know about them now. In the next module, we're going to see different models of the structure of the atom. So we're going to study how that has changed over time. But he didn't know that, so he made a mistake there. Number 4, different atoms combine in simple whole number ratios to form compounds, definite proportions, that's that law. In a chemical reaction, atoms are separated, combined, or rearranged. That's why the masses, what comes in, comes out, because the masses of each atom, their average, are the same. So when you have atoms coming in, those atoms will come out at the end with the same masses. They're just going to be part of a new compound. We're going to learn how to do that very soon. So let's look at number 2 in more detail. If you look at carbon in your periodic table on page number 75, you'll see that carbon is in box number 6. Number 6 is the atomic number of carbon. 6 just means how many protons that element has. And I said that elements are different because they have different number of protons. And you'll learn that the number of protons and electrons is the same in an atom. All carbons have 6 protons and 6 electrons. They all act the same way. Chemically, they're interchangeable. But different atoms of carbon have different number of neutrons in the nucleus. So in the nucleus, we're going to have protons and neutrons in a minute. We're going to see in a minute. Next module, we're going to see how that works. But that makes one atom be more heavy than the other. If you have more neutrons, it's going to be heavier. That makes the masses, that means that the masses of different carbons is different. The mass that we have in the periodic table, so the number that's at the bottom in your box, the 12.0, is an average of all the masses of all the different kinds of isotopes of carbon. So you need to know the definition of an isotope. An isotope is just atoms of the same element. So for example, carbon can be carbon 12, 13, or 13. There are different kinds of isotopes. So they're all carbon, but they have different number of neutrons, making one more heavy than the other. There are different versions of the same element. Okay, it's like having twins, but one is heavier than the other. Okay. So know that difference there. Number 3 was also wrong. He didn't know any better, so he didn't know that we could divide atoms into smaller particles, neutrons, protons, and electrons, and we'll see how that was discovered later on. Different scientists have contributed to the understanding of the structure of that atom. We'll be learning about it. Know what the meaning of fission is? Fission is a nuclear process that breaks down the atom into subatomic particles. You can break down those particles by a process called fission. Just breaks it down. Just know that. Have we ever been able to see atoms? No, we have not. But their existence explains our world, so we believe them to exist. On page, let's see what page is in your book. On page 84 in your book, figure 3.2, you have a scanning tunneling electron microscope image of the surface of a nickel foil. So this represents different atoms inside the foil. But we have never isolated an atom and seen all those particles. We haven't been able to see them, but we have seen the effects of the different particles in experiments. Okay. Now, what we have learned so far, and you need to know the difference between all of these things. Atoms versus molecules, compounds versus elements. Elements, remember, is everything that you have in the periodic table. You have more than 100 of them, 92 you can encounter in nature. It's the smallest amount of an element. So each one of these balls represents an atom. Elements can be in atom form or in molecule form. Molecule means that you have more than 2 atoms that are bonded. That's what it is. It's just more than one. So some elements in nature appear in groups of 2 atoms. Some molecules are not of the same element. They have different elements represented by different colors. When you have different elements, you have a compound. Okay? So you need to know the difference between all of those. You're going to also be learning about mixtures versus compounds. There's another chapter that's going to talk more about mixtures. But a compound right now, remember, a compound is there are molecules that require bonding between the atoms. If you have atoms that are bonded to create molecules, and then you have lots of the same kind of molecules, you have a compound. A mixture, on the other hand, you can have several compounds together, so several different kinds of molecules, or you can have atoms, but they're different. So you see, it's a mixture of, this probably is oxygen, this is probably hydrogen. Here it is, oxygen and hydrogen. So you have, in the same space, occupying the same space, different molecules. Okay? There you go. Let's learn about chemical formulas. You are learning the chemical symbols for the different elements. On the last page of your chapter, you have a list of elements. You're going to be learning them in groups of 20 You have them on Quizlet. You can learn that way. You can make your own cards. I don't care how you learn them, but you need to know the names of the elements and their symbols. So we can do stuff like this. We can write equations. So we have sodium plus chloride to give you sodium chloride, which is stable salt. We need to be able to do that. And I need to be able to say sodium, and for you to just write Na, to know that that's how you abbreviate sodium. It would take a long time just to write every single word to do a chemical equation. So you need to know the definition of a chemical formula, a way of writing one molecule or a compound. This is a chemical formula. This is a symbol, and that's a chemical formula, abbreviation of a compound or a molecule. Things you need to know, besides knowing symbols and chemical formulas, you need to know what those little numbers are called. Those are called subscripts. So a subscript just tells you how many atoms of that kind you have present. So you have 2 chlorines present here. In water, that 2 means that you have 2 hydrogens. Not having a number implies that you have a 1. That just means 1 oxygen. Okay? We're going to learn that when we're writing compounds, we're going to learn how to name compounds and how to write compounds. Metals, remember the last week we learned about metals versus non-metals. Metals are always named first if you have a metal. Let's look at example 3.3 on page 86. With all the information that you have learned so far, what can you do? Well, what is the chemical formula for a molecule that contains 1 atom of sodium, 1 of nitrogen, and 3 atoms of oxygen? And then these, how many atoms are in this molecule? You need to be able to do stuff like that. They didn't give you a name, but they gave you the atoms. And if they give you the atoms, assume that they are in the order when you write them, in the order they give you. So how do we solve this? Okay, just write down what they say. The first thing was the sodium, write the chemical symbol for sodium. Is 1 atom. 1 atom, you don't need any subscripts. 1 atom of nitrogen. Nitrogen is an N. So no subscripts either because it's 1. And then it says 3 atoms of oxygen. Oxygen is an O, and then you need to put a subscript 3. And that is all they're asking. Because you didn't have a name or anything like that. They just give you the atoms. Assume they are in the order they want you to position them. And then read the number and put those subscripts here to tell me how many of each you have. The second part just says count how many atoms you have in that molecule. So I'm going to separate them a tiny bit so you can see them better. To be able to do this, you need to know the symbols. And you need to understand that this is a symbol, that this is a symbol, this is another symbol, and that's another symbol. And then you just read the subscripts. You have 2 plus 1. If there's nothing, there is a 1. Another 1 here, and here's a 4. So put them all together, and you'll see that it has 8 atoms. So even if you don't know the names, you haven't learned them yet, you still can count atoms in a molecule. You're going to do on your own to do these on your own. Okay. We're going to start learning about ionic compounds versus covalent compounds. Remember that compounds requires you to have a bond between atoms that are different. To be able to name compounds, you need to know if the compound is ionic or if it's covalent. One of the first things you're going to learn is physical properties of each. So not chemical properties, not how to read a chemical formula and know if it's ionic and covalent, which you're going to learn. But by physical means, if you could do an experiment, tell if it's ionic or not. So crystalline solids, melting point is high. It conducts electricity as a liquid. Soluble in water means it dissolves in water, and when it does, it conducts electricity. If it can do all of these things, it's ionic. Covalent, because it has liquids, gases, and solids. They have a very low melting point, so the temperature to melt it is very low. Should not have gone forward, sorry. Okay. They do not conduct electricity as a liquid. They have low solubility in water, so they don't dissolve very well, and they don't usually conduct electricity in water. Sometimes they do, some of them do. What physical properties do you need to memorize? The ones in the boxes. So if they dissolve or not in water, yes, no. and if they conduct electricity or not. Yes, no. Yes, ionic. No, covalent. You need to know that. A myth. Water is a covalent compound, but it does conduct electricity. Well, pure water does not conduct electricity. The water that comes out of your tap has metals in it. Once it has metals dissolved in it, it's not pure water anymore. And now it will conduct electricity. So if you drop your hairdryer in the bathtub with you while it's blocked, you're going to get electrocuted. It's just like that. You're going to perform an experiment in which you're going to have several compounds, and you're going to have to divide them into ionic and covalent by studying if it dissolves in water or not, and then if it conducts electricity or not. So if you don't understand this, you do this before you turn in your lab report, ask me questions. Okay, this is what we covered just a minute ago. Now you need to also know the chemical composition of both ionic and covalent compounds, because to name compounds, you need to know if it's ionic or covalent. So metals, nonmetals, if you remember that from last week, and if you go back to page 75 and look at your periodic table, I'm going to go back to 75 too. You know that nonmetals are the pink elements in your periodic table, while the metals are your green ones. So ionic compounds have both a metal and non-metal. You have a pink element and a green element. You just have to find them in the periodic table. If they have a metal, they are ionic. A covalent compound is formed out of two non-metals, so all of them are pink. When you look at the atoms, they all belong in the pink section of your periodic table. And that's how you can tell just by looking at the formula if something is ionic or covalent. Let's do extra practice problems number 2, 3, and 4. The first ones are just theory, so let's see if you can understand them. I'm going to read them to you. Number 1 says, how can you experimentally determine whether a compound is ionic or covalent? Well, if you're doing an experiment, this is what you need to be doing. You need to be looking at the physical properties. Is it soluble or not in water? Does it dissolve or not? Does it conduct electricity or not? If it's yes, it's ionic. If it's no, then it's covalent. That's all you have to do. That's like the experiment that you're going to be doing this week. Number 2, how can you determine from the periodic chart whether a compound is ionic or covalent? Well, if you're using the periodic table, you're doing this. You're trying to figure out if it has metals. If you see metals, ionic. If everything is non-metal, covalent. Number 3, let's look at number 3, and I'm going to use the board to do that one. For number 3 says, which of the following molecules are covalent? So number 3, let's look at the first one, SO2. Where are those two atoms in your periodic table? S is in column 6A, O is in column 6A. Both are pink. That meant non-metal. That means it's covalent. See that? B is magnesium and chlorine. So magnesium is found on column 2A. That's green, that's a metal. That is non-metal, is in column 7A. But the presence of a metal makes this into an ionic compound. Okay? So covalent, this one is covalent. You have to say A, B does not belong. What about C? Sodium and chlorine again. Sodium is in column 1A. That's green. That's a metal. That's directly ionic. You even have to look at the other one. If you have a metal, it's ionic. That doesn't belong. So D, C2H4O. Where are they? Carbon is in column 4A. H is in column, I'm reading the numbers at the top of your periodic table on page 75. That is in column 1A, but is pink. Anything pink is non-metal. And oxygen is in column 6A, so it's non-metal. All of them are non-metals. That makes it covalent. So in your answer, you should have to say A and D. So these ones are the ones they wanted to know about. 4. Which of the following molecules are ionic? You will be doing exactly the same thing. So A has nitrogen and oxygen. that is covalent, does not belong. Okay. Maybe I should just make you do this on your own. Okay. The next one is Rb and O3. You have a metal. First one is Rb is a metal. It's in column 1A. That is ionic. pH3. Both of them are nonmetals. That is covalent. So that does not belong. And then you have sodium S for sulfur and O for oxygen. I'm sorry, I'm reading them as names, but you have probably not learned them yet. So NaSO4. So what? You have sodium and A, and that is a metal, and that makes it ionic. So your answer should have been B and D. And that's how you do these kind of problems for this section. Okay? Now, let's learn how to name ionic compounds. You are going to have rules both for ionic and covalent compounds. They have two different rules. These are the easiest of the rules, and the covalent is based on this. So you have to learn this one first. Page 90 has the rules. In a binary ionic compound, so a compound that has only two atoms, you're going to have a metal and a nonmetal. You are going to name the metal first. Just read the name of the metal. And for the nonmetal, you're going to change the ending to "ide." For example, aluminum fluoride, calcium nitride, potassium chloride. You name the first one, the metal, just directly from the names that you are learning, okay? And the next one, it's not always just take the last two letters and add "ide" to it. Sometimes you have to change it a tiny bit more, like hydride or oxide. So these are a couple you're going to have to learn how to spell them. Because oxygen, if you take just the EN out, there's a lot more letters left, but you don't use that. You use oxide. And hydride is the same kind. Pretty easy to name. Now, the same thing here is another example. We saw that before. Always the metal first, non-metal second. Name the metal, and the other one ends with "ide." What about covalent compounds then? I said to you, the first thing you need to do is be able to tell if it's ionic or covalent before you can name them, and then apply the rules. You would name them like you would name an ionic compound, but you're going to have to tell me how many atoms you have of each kind. You have nonmetals, so how many you have of the first, how many of the second. By using prefixes. You probably know these prefixes from geometry. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. And if you have not memorized these, you will have to memorize it. You always have to give me those, remember the suffixes, those little numbers? When you have covalent compounds, those suffixes you need to name by attaching this prefix to the name of the atom. You will do that for everybody except the first atom if it's mono. So the first atom of the molecule, if it's mono, if it only has one, you will not say it's mono. You're going to leave it alone. If it has two or three or more, you're going to have to name it. How does this work? Let's look at this, okay? It's a lot easier to see examples. So sulfur had only one. Remember that if the number one is missing because we don't put ones, we just don't. So we just name it sulfur. This one ends with "ide," oxide. But how many of them are there? Two. The word prefix for two is D. Sulfur dioxide. So you're using the same thinking you were using for ionic compounds, but now those subscripts need to be mentioned. Now, nitrogen is not one, it's two. That means you need to mention that. The only one you can skip is if it's the first one is one. So D, nitrogen, one oxygen, monoxide. Mono always is used for the second one. Not for the first, but the second means the mono. Carbon, tetrachloride. Nitrogen, but how many? Two. Dinitrogen. Oxygen is going to be oxide. How many? Penta. Pentaoxide. Dinitrogen pentaoxide. Okay, nitrogen here. How many? Two. Dinitrogen. This is going to be named oxide. How many? Four. Tetraoxide. Mono, you don't need to mention that. So just oxygen. Two of them. This is fluorine. Take the in out, add fluoride. How many? 2, difluoride. And that's something you need to be able to do from now on. So for example 3.4 on page 92, it says name the compounds whose chemical formulas are here. To name anything, the first thing to do is divide them. Are they ionic or covalent? So decide. This has a metal, this is ionic. So you're going to follow the rules for ionic compounds. Aluminum oxide. That's it, aluminum oxide. This one right here, there's no metal, this is covalent. That means those little prefixes need to be used. Mono will not be used, but you will be using tetra 3 here. So phosphorus 3 hydride, and you're done. You try this, please, by doing 9 and 10 on your own, and I'll help you here. So 9, it's telling you to give the chemical formulas for the compounds mentioned to you. So number 9 is going to be easier. I'm not going to be able to just tell you and just move on. I'm going to tell you. Diphosphorus. D means 2. Phosphorus, you need to find the chemical formula is P, so D is 2. And hexaoxide means you have 6. Oxide is O6. That was A. B, the nitrogen tetrahydride. Nitrogen is an N. D means it has 2. Tetrahydride, you have a hydrogen. How many? Tetra means 4. This could be closer together, okay? But that's okay for right now. Nitrogen monoxide. Nitrogen, if it doesn't have the monos because it's 1. Monooxide, it means it's also 1. And that's it. That's all you have to be able to do for this. So number 10. For number 10, now it says give the names of the following compounds. So remember, rules are different depending on their nature, ionic versus covalent. So SO2, covalent or ionic? Well, that is a covalent compound. Okay? So we're going to use our covalent rules. That would be sulfur. There are 2 of them. D, oxide. Ends with I, just like ionic, but we needed that D in there. B. Okay, we have a calcium, a chloride, a 2. So we do have a metal that's ionic. That means just name them. Calcium. No prefixes needed here. And then chloride, and it's to end with "ide." All of them end with "ide." C. What do we have there? An oxygen and chlorine again. So those are nonmetals. We have a covalent compound. So just oxygen, because we don't need to put mono for the first one. And the other one has 2, so D. All right. Okay. And we have one more. The other one has sodium and it has sulfur. Sodium is a metal, so we have an ionic compound for this one, and we need to use the rules for ionic, and that's sodium sulfide. And you're going to be practicing this week. So that's number 10. And that concludes module 3. Read your textbook, add your notes, review examples as you need to. Do on your own as you encounter them, correct them as you encounter them so you don't make the same mistake, ask questions if you need to, study for your conceptual quiz. Remember that some of the quizzes are going to be now on elements and their symbols. Do labs assigned for this section, do the review questions and self-correct, do practice problems and self-correct with answer key first, and then social manual if you cannot figure it out. And of course, I'm here to help you. So join me for a Zoom meeting if you need. Or Zoom, I don't know what I'm going to use, probably Zoom, but whatever virtual meetings we have, join me to ask questions so I can help you. I hope you have a good week. Bye-bye.